Section 4.1. Here are our objectives. Number 1, evaluate exponential functions. Number 2, graph exponential functions. Number 3, evaluate functions with base of e. And number 4, use compound interest formulas. Okay? So first of all, evaluating exponential functions. Remember, if I give you a function like f of x equals 2x plus 5, I know this is not exponential. I'm just giving you an idea about evaluating, just reminding you about evaluating, okay? What if I ask for f of 3? What am I asking you to do? Plug in 3 for x, right? So 2 times 3 plus 5 would be 11, right? So evaluating an exponential function would look like this. 2 to the x power plus 5. So again, if I ask for f of 3, I'm just saying 2 to the third power plus 5. Well, 2 to the third power is what? 8 plus 5 is 13. F of x is 3.5 times 2.3 to the x power. What if I ask for f of 4? Now, is that something you could do in your head? If you are, you're amazing, just like always. But we may need to resort to our calculator this time and say 3.5 times 2.3 raised to the fourth power. Okay? So that would be 3.5 times 2.3 raised to the fourth power, and that it would equal 97.9444. And I just need you to pay attention in your directions, in your instructions on each problem, how to round it. It may say round to the thousandths. It may say round to the tenths. Just pay attention what they ask for, about how they want you to round it, okay? Got it? So, just as a reminder, okay, if I ask for f of x equals 2, are you guys okay with evaluating exponential functions? Okay, so graphing exponential function is our next objective, okay? So 2 to the x power, what I need you to remember here is what it looks like, first of all. We got two examples here, okay? The first one here, this is called exponential growth. And it's called exponential growth because it is increasing from left to right. Do you see that? Our base, whatever number this is, and in this case it happens to be 2, but our base is greater than or equal to, greater than 1, not greater than or equal to, just greater than 1. Okay? So maybe it's x to the y power. Well, x has to be greater than 1 for it to be exponential growth. Does that make sense? Okay? This other graph down here, this would be f of x equals 1/2 to the x power. Okay? And this is called what? Do you remember? Exponential decay. And do you remember why it's exponential decay? It is decreasing, right? From left to right, it's decreasing. Now this base is between 0 and 1. I don't know why I keep putting equal to. It's not equal to. It's between 0 and 1. Okay, it has to be greater than 0. A base of 0 is nothing, right? That's just 0. And a base of 1 would just be 1 to any power is always just 1, so it would just be a horizontal line. Okay? So that wouldn't be anything really exponential. Okay? So if I give you, well, do you remember your transformation rules first of all? So let's just go straight to a nice, long, hard problem. How about that? I know you're so excited when I do that. -4 times 1/2 to the x plus 3 power minus 2. What I need you to remember is what all of these things do. Okay? First of all, what is the parent function of this transformed function? Well, it's called g of x, the parent function. That would be 1/2 to the x power. Okay? It'll have the same base as this function. The parent function will be 1/2 to the x power. So first of all, tell me what this does to the function. This reflects it over the x-axis, right? The negative in front reflects it over the x-axis. What does the 4 do to it? So this causes a vertical stretch. Okay? Now I'm going to put in parentheses or compression. The multiplier is what causes the vertical stretch or compression. For this specific example, it is a stretch because it is greater than 1. That's exactly right. Okay? By a factor of 4. So for this specific problem, it is a vertical stretch. But remind yourself that the multiplier can also cause a compression. In this case, it's a vertical stretch by a factor of 4. Okay? What does the 3 do? Can you tell that that's inside the exponent? Well, if it's inside, what kind of change does it cause? This causes a horizontal change. What kind of change? A shift. Now this particular horizontal change is to the left 3. Remember, when it's inside, it's opposite of what you think it would be. It'll move the opposite direction. So you think it might be to the right 3 because it's plus 3, but it's really to the left. Okay? We know horizontal shifts can move to the left or the right. This particular one moves to the left, correct? Okay? And we got one more thing to deal with. The 2, right? Can you tell that the 2 is outside of the function? Okay, so what kind of change does it cause? Vertical change. This particular kind of vertical change is a shift. Vertical is going to move up or down. This particular one is going to go exactly where you think it should go. Perfect. Down 2, in fact, correct? Any questions about that? If I give you a graph, could you match it to the correct graph? And you could either use your brain or, your calculator. Okay? How are you feeling about graphing exponential functions? Oops, sorry. Do you remember your transformation rules? Good. Let's talk about evaluating functions with a base of e. Okay? First of all, I want you to know some stuff about e. I know that your whole life you've been told that e is a letter. That's because it's true. Okay? But we also use e as a number. It is not a variable. It has a set value. Okay? If you look on your calculator right down here, it's even a button on your calculator. If you press e to the first power, let's go ahead and press enter. It tells you the value is 2.71828. Okay, and that's an approximation. That's a rounded answer, 2.71828. Okay? Any idea why we call it E? I don't know for a fact, but I have an assumption. This number, I don't know if discovered is the right word. This number was discovered by Leonard Euler. And, or I don't remember if I'm supposed to say Euler or Euler. Dr. Potter would be so mad at me for not knowing about that. I'm sorry. But it's a pretty famous number. It's used in a lot of places. It's seen in a lot of different places in nature, which to me makes it really cool because he didn't come up with it, he just discovered it, like I said. Does that make sense? Yeah, I'm pretty sure it's supposed to be Euler. So, not that Dr. Potter would ever watch this, but I apologize, Dr. Potter, for forgetting. Okay? I just in case you're curious, 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial, and on and on and on. That's where the number comes from. Okay? So, can you evaluate functions with the base of e? So if I say f of x equals 4 times e to the 5x power, and then I ask for f of 2, surely you can do that because you have a calculator. In Spanish, calculadora, yes? Okay, 4, remember it's right here? Sorry, right here. E raised to the what power? 10th, right? Because it's 5 times x, and our x is 2. So we would say that this is 0.5.9. And again, that's rounded, so you just have to check your instructions to see how far you want it rounded, yes? Okay. Do I need to do any more examples of evaluating functions with base of e, or you got that? You got it? Okay. Feeling okay with evaluating regular exponential functions and then also functions with base of e? Feeling okay with graphing exponential functions? Okay, compound interest formulas. There's 2 compound interest formulas that I need you to know. A equals P times 1 plus, not times, yes, 1 plus R over N to the nt power. That's the first one. That's the second one. Yeah, I'm sorry. Okay. So to be clear, this particular interest formula is when the interest is compounded, compound, compounded a certain times of month. Sorry, certain times, and I'm going to put ... because it's not just per month, but it could be per year, it could be per week, it could be per day, things like that. So it's interest compounded the certain times of however many it tells you. Okay, this kind over here is interest is compounded continuously. So all the times you're constantly earning interest. Okay? Either formula, either one that you look at, A is the amount that you want to end with. Okay? In fact, the amount of money that you end with. P is the principal, not like Mr. Acevedo, okay? But the principal or the amount of money that you start with. Any guesses on the T? Time. And it will be in years. So if it's given to you in months, you got to convert it. If it's given to you in weeks, you've got to convert it. when you enter t, the number for t, for time, it's got to be in years. Okay? What about the r? It's the rate. It's the percent, right? It's the interest rate. So if it tells you 6% interest rate, what do you have to do? You need to convert it to a decimal, don't you? Okay, please don't forget to do that. And N. There's not an N in this one, okay, but there's definitely an N here and here. It's the same value both times. It's the number of times per year. That the interest is compounded. Okay, the most popular ones would be yearly, monthly, weekly, and daily. Yearly, monthly, weekly, and daily are the most common. I'm not saying that there aren't other ones, but these are the most common. If we're dealing with yearly, what is N? If it's the number of times per year that the interest is compounded. 1. What if we're dealing with monthly? 12. What about weekly? 52. And what about daily? Yeah, we don't hardly ever take into account leap year for interest. Okay? So we use 365 for interest, even if we're in a leap year that we're currently in. Right? Okay? Now, I didn't do any examples of these, but I gave you both of the formulas and what everything stands for. Is that okay? Okay. Any questions about any of these objectives? Got it? Sorry, there they are.